The main building block in modern visual perception systems is the deep convolutional neural network. In deep learning, we shift much of the effort of building good models to the task of constructing large annotated datasets, and we use mechanisms for the model to be able to train itself to achieve the task by seeing lots of examples. In this video, we will do a relatively brief introduction to neural networks. For a more expansive treatment, please see the links on the edX page. The basic building block of the neural network is the neuron. Inspired from our understanding of the brain, the neuron has a relatively simple structure. The inputs to the neuron are weighted, summed, and passed through a nonlinear differentiable function called an activation function. There is also an optional bias term, which is shown here. These basic building blocks are powerful. For one, they can be composed together to create a larger structure. A second key property is that the input-output relationship is differentiable. This will be a key feature for tuning weights and biases, which are the free parameters of the model. In fact, these two properties give us all of the tools we need to understand how these models get trained. Let's take a toy example of the neural network with 3 inputs and 1 output, together with one hidden layer with 3 neurons. In reality, these networks are much bigger. In the case of visual perception, each input neuron represents a pixel. So already for a 640 by 480 image, we have over 300,000 inputs. But let's just consider this small case for now. The one output makes this a binary classification problem. For example, we're trying to determine whether or not a ducky exists in an image. This type of network where every neuron is in one layer is connected to every neuron in the next layer is called a multi-layer perceptron, or MLP. Here, the output y is predicted by running the input x through the model f, which is parameterized by the model weights w. Note that we have omitted the biases just for notational simplicity. At first, the weights are randomly initialized. How do we figure out what good values are for these parameters? Crucially, this is where our dataset comes in. We are armed with a bunch of examples of images where somebody has manually annotated whether there's a ducky in them or not. So we can apply the input to our model. At first, we will just get a random output, but we can compare the output predicted by our model to the real value annotated by a person and calculate the discrepancy. This discrepancy is called a loss, and the function that we use to calculate this discrepancy is called a loss function. We want this loss function to be larger when the prediction is further away from the ground truth, and smaller when it's closer. A function that is simple and satisfies these criteria is simply the absolute value of the difference between the ground truth value and the prediction, otherwise known as the L1 loss. A more commonly used loss function is actually the binary cross-entropy loss, shown here, which causes the network to train more quickly because it penalizes more heavily predictions that are further away from the correct answer. Here we have shown the graph of the two functions for a ground truth value of 0 with the model prediction on the x-axis. Now that we have this loss value, we want to adjust each of the parameters or weights in our model a little bit to reduce the error. What we want to know is how much each weight contributed to this error. Written in math, we want the partial derivative of the loss with respect to the weight. This tells us how much the loss will change if we change that weight. Since each of the neurons is input-output differentiable, we can calculate these partial derivatives by chaining all of the individual partial derivatives together. This process is referred to as backpropagation. We decide how much to adjust each parameter in the model in a way that's proportional with the magnitude of the gradient. This was just for one training example. In practice, we want to perform this procedure over the entire dataset and repeat many, many times until the values of the weights have converged. Once the model has converged, we can hope that when we present it with a new example that it has not seen before, that it will give us the correct prediction. We should understand that what we're really doing here is solving an optimization problem. We're trying to find the optimal weights such that the loss function is minimized over our dataset. The method that we have just introduced to solve this optimization problem is very classical and is called gradient descent. In gradient descent, you update the parameters in the direction of the negative gradient multiplied by the step size. This step size is a very important parameter. If it's too small, it can take a very long time to converge to the optimal solution. If it's too big, you can jump around and never arrive at the optimal solution. The picture of our loss function here is also not very realistic. Most important is that the function here is convex, meaning that it has one unique global minimum. In practice, the functions that we are optimizing when we train neural networks are not convex at all. This can lead gradient descent to get stuck in a local optimum that can never escape because the gradients are zero. This is another consideration when tuning the step size. We want it to be big enough to jump over these local minima. In theory, we should evaluate the loss on every element of our dataset before taking a gradient step. But this can be very slow. In practice, we randomly sample a batch of data and use this batch to approximate the gradient. This process is called stochastic gradient descent, since there can be some noise on the actual gradient. We should make another comment about the dataset. If we optimize too much on our training data, we will not generalize well to new test data. This is a problem called overfitting. To mitigate this problem, it is standard practice to separate our dataset into two parts, one for training and one for testing. We only use the test data to evaluate the model, never to update it. That way we know that when the performance starts to go down on the test data, we are just overfitting to our training set. One component that we skipped over at the beginning that can have a huge impact on what the loss function looks like is what we choose for the activation function. The simplest choice is the linear activation function, but this is rarely used in practice. A popular choice is the sigmoid function. As we can see, it has a nice smooth derivative. Another popular choice is the hyperbolic tangent for similar reasons. The problem with these two functions is that when the input is not near zero, they are both very flat, a problem called saturation. The result will be that the gradients will become very insensitive to the error and learning will become slow. This led to the introduction of the rectified linear unit, or ReLU. This function can be seen as more like a gate. It passes its input through if it is greater than zero and sets it to zero if it's less than zero. We can also see that the ReLU function does not have this saturation problem in the positive direction. Neural networks are the core building blocks of most modern AI systems. In some respects, we're still trying to understand exactly why they work as well as they do. This has been a relatively high-level overview of the basic mechanisms for training neural networks. However, by far the most important factor in model performance is the quality and size of the dataset you are using for training.